Like the first section of this chapter, this one is totally informational. It is describing to you the VSEPR model. That stands for valence, shell, electron, pair, repulsion. And what does that mean in English? Well, that's what we're going to try to explain to you right now. When we make a covalent bond, we know that a pair of electrons is definitely shared. We learned that in the last chapter. Now, there's some new terminology. One of them is the words electron domain. And that's the region where the electrons will be found. I'll have a picture of that in an upcoming slide. If we have what is called a bonding electron pair, it will be the ones that are involved in the covalent bond. If we have a non-bonding electron pair, I'll use the terminology non-bonding, that's where electrons are located on one of the atoms. And I've been making the electrons, and I'll draw a little circle around them just so that you can spot the non-bonding. Now, there are 5 ideal geometries, and they are going to give rise to 11 different shapes. In the first section, remember we saw something that was linear, which was CO2, and then we saw something that was bent, which is SO2. And because one ideal geometry can give rise to more, there actually are 11. So you saw I call them the mother geometries on the first slide. So this is just another picture. Spend some time and look at what do these shapes look like. Notice what they call the number of electron domains. And this again is ideal. 2 electron domains because we're going to be sharing an electron in this orbital and an electron in that orbital. And that ideal will give rise to a linear. It goes all the way down. And if we were in class, I would have some party balloons. And I would have someone take a pin and I would have them break party balloons. We normally start with 6. We go down to 5, but your book begins with 4 party balloons. Oh, excuse me, 4 different electron domains. And if you were to break one of those balloons, what you would come up with the 3 electron domains, break another balloon, you would come up with the 2. And you will see this is linear, this is trigonal planar, and the last one is, we abbreviate it, TH. Tetrahedral. Now, most of the things you're going to encounter in our class are going to be 2, 3, or 4 electron domains. In the field of inorganic chemistry, there are a lot of 5 and 6 electron domains. Actually, the hemoglobin that transfers your blood, it is going to have 6 electron domains, just to kind of put something in. So, that is the ideal, and what we will talk about a lot in this class are derivatives of the tetrahedral. We're going to show you how they are derived, but for now, I'm going to say, here's a tetrahedral. It represents methane, and if I take away one corner atom, and that's this red arrow, what I would be making is NH3, and I would still have a lone pair of electrons there. So this is really my poster molecules, I always call them. I can talk about methane, where I have a tetrahedral. I can take away one corner atom, and I will go to a trigonal pyramidal. And then if I take away one more corner atom, I will go to what is called the bent shape. Now you're going to say, who cares? Hey, OH2 is water, H2O. So these materials you're going to speak about a lot when you take a full year course of organic chemistry, where you've got a carbon or a nitrogen or an oxygen. Think about the human body and all the molecules in it. They are made up of carbons and oxygens, hydrogens, and nitrogens. So again, very, very powerful. So again, this is a teaching segment. When we talk about a bonding electron pair, it's going to be attracted by 2 atoms. And there we have an artist's rendition of a bonding electron pair. You see the nuclei, and the blue in between is the area where the bond forms. But what about if we have a non-bonding electron pair? Well, that's going to center on only one atom. So all they drew in was a nucleus, and notice how much more space it takes up. So whenever I have a non-bonding electron pair, they are going to compress the bond angles. So here I have my methane, my ammonia, and my water. And you notice methane, we have all bonds and our bond angle is 109.5. With ammonia, we have one non-bonding and that causes that angle to compress to 107. When I go to water, where I have two non-bonding, what I go down to is 104.5. Now, you'll have this fact here in Gen Chem. You'll have this exact same fact when you take organic. So if you get it into your deep memory now, you can just call upon it next year when they're going to be teaching much harder material. The last thing I have in this section, again, this is all informational. It is just the pictures. We have our electron domain geometries, 2, 3, 4. Here's our other 2, 5, and 6. Remember we said we have 5 ideal geometries. As you can see, depending on the number of non-bonding electron pairs, we can come up with many other geometries, and that's what's to come in the next section. You will be given a molecule. You'll have to draw the Lewis structure. You'll have to designate the bonding and non-bonding electrons. You'll talk about the electron domain geometry, the molecular geometry, and let's not forget whether it's polar or nonpolar. If this is your first time going through it, it's going to take some time. If not, it will be a refresher.